Welcome back to the third video in the space-time or special relativity in geometric algebra series that I'm doing. I wanted to go back and clarify a mistake I made in the last video. In the last video, I added a negative sign here. There shouldn't have been, so this is actually the correct form. There's no negative sign up here. My bad habit in geometric algebra is adding negative signs where they shouldn't be. So now that's fixed. Then we also get rid of the negative sign here. And we actually generalize this to, before what I had written was phi v hat plus b for some bivector b, but the most general form is actually w, some vector v, or w, and then minus a, because this minus sign for the bivector a comes from the fact that we put the minus sign up in the rotor, the Euclidean rotor, but for the hyperbolic rotor we don't have a positive or a negative sign, so we don't. And everything else in that last video of which I talked still holds. Okay, so now let's go into spacetime rotation rates and eigenspinors. So what is an eigenspinor? Well, in the context that we're talking about here, where you have some paravector that's been mapped to, we'll say that we're going from rest and we're mapping it to a equal to lambda a rest, lambda dagger. So that's the first mapping. But say that we're going to do some other Lorentz transformation, and I'll call the next Lorentz transformation, I'll do the squiggly L. So say then we map from Lorentz here to another lab frame. This will map to, I'll call this just A prime, which is equal to lambda L, or lambda L lambda. I got my words mixed up there. Rest, then everything daggered here. Well, you'll see that by rotor composition, you have this whole thing here. All daggered. Now, moving the paravector into this new frame with L requires a sandwiching. But this can be thought of equivalently as L mapping or changing lambda to a different frame. And so it can be thought of as this mapping right here. Lambda maps to L lambda. And this is similar to other forms of spinors in physics. And so because of this form existing, it's called the Eigenspinor. And eigen being a word from German meaning like own. It's cognate with the English word own, so it's the proper spinor. Just move this and put this right there. Now, that's more so the background for the nomenclature, but how do we actually use this? Previously, I had given that the Lorentz transformation from the Lorentz rotor, or the eigenspinor lambda, is equal to e to the 1/2 omega t and lambda naught. Well, actually, this is a solved version of, so this comes from a differential equation where you assume that the time derivative of this eigenspinor is 1/2 omega and then itself. Where in this more abstract version, you assume that you don't actually already know what this is. But when you solve this, in general, you get this more trivial solution just by, putting this under there and then exponentiating or integrating, you get natural log, and then you get after taking the exponential, you get this result right here. But that's not the important part. The important part comes from this. This is a differential equation of the spinor, and this determines the entire dynamics of a relativistic particle. How so? Well, let us look at momentum and then derive a general force equation for this, or rather, from this. So we know from the definition from last week's or yesterday. I keep saying yesterday, last video. It's just the last video that I released. That momentum is given by, or I should specifically say, for momentum is given by the paravector P, which is the eigenspinor MC lambda dagger. Well, this can be rewritten. You can, because these are scalars on the inside, you can actually take them out. So I can rewrite this as M lambda C lambda dagger. Well, we know that from just basic physics courses that the momentum is equal to m times the proper velocity, defined as u. So what this implies, this implies that the proper velocity u is equal to lambda c lambda dagger. And this should make sense looking at the diagram here. If you're traveling at c, you can only travel at c if you're massive and going straight. And so if you have any sort of deviation from going straight, then you're going to gain components in other directions. And that's exactly what is encoded in this. It's just rotating a straight line going towards C in the other directions and giving it components in spatial directions. So that is the proper velocity. And the reason I define it now versus later is because this will be useful in simplifying the generalized force law. So let's consider the time derivative of the momentum. Pulling out an m, this will just be the time derivative of lambda c lambda dagger plus lambda c lambda dagger dot and this comes just from the product rule of differentiation. But we know from the differential equation of the spinor that we can just substitute this in. So this is equal to m and then 1/2, which can be just simplified as m over 2 omega lambda c lambda dagger plus lambda c lambda dagger omega dagger. Now, how did I get this last one here? Well, that comes from this. If I take the reverse of this, then I get 1/2 omega lambda reverse is equal to 1/2 lambda reverse omega reverse. And so this is why I can do this down here. So then I can close that up. And then I'll just simplify this, reduce some stuff. You get omega u plus u omega dagger. But how do we simplify this further? Because this looks like you're trying to, like I'm trying to create some cross product definition or some inner product definition, some product definition. But this little dagger up here throws things a little weird. It makes things a little weird because I can't just do the traditional definition where you have AB plus or minus BA, because this makes it different. It's like having an A dagger up here, which changes how this equation works. So then what do we do? The next step is to actually expand out this space-time rotation rate, which if I didn't name before, that's what omega is. It's the space-time rotation rate. And that's why it's in the title here. So the space-time rotation rate, I'll just write this out here so we have it for reference. Omega equal to W minus bivector B, bivector A, sorry. So this becomes M over 2 of W minus A U plus U W. But then, because there's this dagger up here, it's plus the bivector A. And if you're confused why it doesn't affect this W, it's because it's a vector. You can't reverse a vector. That is, that W vector dagger is just W vector itself. So you have this equation. Now, I'm going to pull this over here and then continue expanding this. So then it's M over 2 of W U, or WU plus UW plus UA minus AU. Close that out. Now these are starting to look like cross product, or like inner products. Well, actually, inner product of a bivector and a vector, inner product of a vector and a vector. However, not quite. Remember that U is an element of 0 plus 1. It is a paravector. It has a scalar component to this 0. So we can't just say that these are those products. Not quite. Not yet, at least. So the next thing is to actually break U into its component forms. Well, for now, we won't be explicit about what they are. We'll just call them that. So, like I have it up, like I have the spacetime rotation rate right here, I'm going to put U as being equal to the time-like component plus the vector, like space-like vector. But that, I don't like this notation personally. I prefer just saying the projection of it onto its vector components. So that's what I'm going to write. So this would be the scalar component. This will be the vector component. So we can then expand it out again, doing a lot of algebra. But hopefully this is enjoyable for, a lot of people. If you're doing this to the point where you actually need to learn this, then you probably enjoy it at least to some degree. Like I know I do. So we can have W. And then you have ut plus u1 plus ut plus u1 w. And then actually this is going to go off screen if I do that, so I'm going to move it a little bit just to give myself space. But then continuing plus, then we have the u on the first side here, plus ut plus u1 a minus a ut plus u1. And this closes. So, oof, that looks like a lot of squiggles, but luckily the colors make it a little easier. So, what do we do next? Well, let's separate out all of the bivector products and the vector-vector products, and then all the scalars. So then we can actually do some simplifications. So, starting to write out the next part. Well, if we notice here, we're just going to get 2 times, because this is a scalar times a vector, and we have a scalar times a vector here, we're going to get 2 times, I'll write it like this, we're going to get 2 times utw. Now I was right the first time. Let's do it like this, 2utw. Then we're also going to get 2, and then because of an identity here, or actually I'll just write out the identity so that you can see it. There is an identity that for a vector a and b, you have this as their inner product. And so we have w times u plus u times w. And that's the same thing as 2 times their inner product, or twice their inner product. So you have 2, then you end up with w dotted with u1. Let me do this. Dotted with u1. And then plus, now let's work on simplifying this area. Well, we have a scalar times a bivector and a bivector times a scalar. The scalar can move on either side, but this one is the negative of the other. So they're just going to cancel out. That is, the scalar times the bivector and the bivector times the scalar will cancel out, so we don't have any of those terms. So we end up only with terms like this. We're going to end up only with terms that look like, u1 times a minus a u1. Well, this is just like this definition over here. This is the definition 1 over 2 of this for the inner product of u1 with a, with the bivector. This is the definition of a bivector-vector inner product. And so we can just say that this is 2 times u1 inner product with a. Then we can close this off with an appropriately sized parentheses. Now, I'm just going to get rid of that. Move this over here. Now, this 2 and 1 over 2 will cancel, so we just end up with m times ut w plus W dotted with the vector component of the proper velocity plus, plus the vector component of the proper velocity dotted with the bivector A. Now, something before I simplify this even further, I'm going to actually replace this dot with a different notation, because this product actually is the same as just taking the cross product of this vector and this bivector. The inner product of a vector and a bivector is the same as the cross product of a vector and a bivector. So I'm just going to write their cross product. Now, what are the general components for this proper velocity? Well, if we go back up to here and look at the proper velocity, we can see that u is equal to this right here. But a classical result in physics is that u is equal to gamma times c plus the velocity in a lab frame, the relative velocity in a lab frame, the perceived velocity. So that is what this is defined as classically. So we can actually plug this in over here. But how do we plug it in? First, you make the identification that the timelike component is just going to be gamma c. That's the timelike component. So you get ut is equal to gamma c. I'll put this little implies sign. And therefore, you get that the vector component of this is going to be gamma v, like that. So now that this is known, it can be plugged in here. Equals m times gamma c w plus w dotted with gamma v plus gamma v cross a. Well, this gamma can just be moved to the front, because in every term here there's a gamma there, there's a gamma there, and there's a gamma there. So then you can rewrite this entire thing as gamma m, and then all of that times c, or times c w plus w dot v plus v cross a. So this is your generalized force law, or relativistic force law. But is this actually of a correct form? Well, I'll give an example that kind of shows why it should be a correct form, and that is if you know the Lorentz force law. So I'll just put this as Lorentz force, so LOR. The Lorentz force law says that gamma of, what is it? It's E, and then the electric field vector plus E times the velocity vector cross B cross B, and then let me put this there just so that that looks a little cleaner, and plus E over C E dot V. So you have this right here, this form for the Lorentz force law. And it should look pretty familiar based off of this form that we have up here. Granted, there are some differences, but let me highlight the similarities. You have the vector by some constant out here, and then you have the vector dotted with V, and then you have V cross some vector. Well, the interesting thing about this is that they're actually equivalent. If you choose the correct, so if you choose the correct omega, then or I'll just say, if you choose the correct omega, then you can get this. So the generalized force law here just describes how some particle will move, some particle with this momentum p will move in some space-time rotation rate, in some kind of field generating this. In an electromagnetic field, it happens to be this. But in general, it's just using these. And I'm going to put this in one final form just to relate it back to what we have as the space-time rotation rate. So this ends up being C W then plus omega dot V. That's what this equation is equal to, and you can prove this step for yourself doing it by hand. And you can further prove by hand that this is just equal to omega, or it would be omega times the momentum p, and then projected onto its paravector components. So this is how you deal with relativistic forces in special relativity using the framework of the Pauli algebra of space in its geometric algebra form.